Hello everyone. Still in part 2 of our module of fundamental physics, part 2 of electricity and magnetism. Today we are going to do exercises on electrostatics. So I'm going to give you a hint on problem solving in this part. Exercise number 1. 3 charges in a line. Three charged particles are arranged in a line as shown in figure below. Calculate the net electrostatic force on particle 3, the minus 4 microcoulomb on the right, due to the other 2 charges. As described in theory, we consider the principle of superposition, where one charge feels an electrostatic force due to the remaining charges. This means that charge Q1 exerts a force on charge Q3 and charge Q2 exerts a force on charge Q3. And we are asked to determine the net force on charge Q3. This is the force F3. This force F3 in vector form is equal to the force on charge 3 due to the charge 1 plus the force on charge 3 due to the charge number 2 in vector form. And here we need to show the orientation of the charges. If we say this is our charge Q3, and then the charge Q3 is negative and the charge Q1 is negative. Since like charges repel, so charge Q1 will push away charge Q3 with a force F31, means the force on charge 3 due to charge 1. And since the charge Q2 is positive and the charge Q3 is negative, charge Q2 will attract charge Q3 with a force oriented from Q3 to Q2. This means that charge Q2 attracts charge Q3, and charge Q3 is attracted by charge Q2. Charge Q3 is repelled by charge Q1. Then, as you see, the magnitude of charge Q3 may be larger than the magnitude of the force that Q1 exerts on Q3. It's the reason why this force on charge Q3 is a force oriented in a negative x direction. And this is how we are going to find an answer. We apply the Coulomb's law, where the electrostatic force equals to the Coulomb constant K times the magnitude of the first charge times the magnitude of the second charge divided by the square of the distance between the 2 charges. Let us say here use indices I and J. The force between charge I and charge J is equal to K times the magnitude of charge I times the magnitude of charge J divided by the distance between I and J. And this distance is squared. Yeah, this is the general formula for Coulomb law. Then here we have our diagram. This means that the force on charge 3 due to charge 1 equals to K Q3 Q1 over distance between charge 1 and charge 3 squared equals K 9 times 10 to the power 9 times the charge 3 minus 4. And then we use absolute values, positive numbers, 4 times 10 to the power minus 6 times the charge 1 8 times 10 to the power minus 6 divided by the distance between charge 1 and charge 3, 0.5 meters squared. Then we see that This force on charge 3 due to charge 1 is having a magnitude 1.2 newtons. This is a force oriented to the right in positive x direction. Then the force on charge 3 due to charge 2 equals to Coulomb constant times the charge 3 times charge 2 divided by the square of the distance between charge 3 and charge 2. Okay, 9 times 10 to the power 9 times 4 times 10 to the power minus 6 times 3 times 10 to the power minus 6 Coulomb divided by 0.2 squared, which gives a magnitude of 2.7 newtons. We are not done. What we calculate now are the individual forces that each of charge 1 and charge 2 exerts on charge 3. Remember, our task here is to find the resultant force on charge 3, which is equal to the force on charge 3 due to charge 1 plus the force on charge 3 due to charge 2, sorry. And then these are first added in a vector form, and we see that the magnitude of force on charge 3 due to charge 2 is larger than the magnitude of the force on charge 3 due to charge 1. And we have F3. 2 is larger than F3, 1. This means that the resultant force on charge 3 will be oriented in the direction of the force on charge 3 due to charge 2, which means that the resultant force is oriented to the left, means in negative x direction. Where we have this force equals minus F32 plus F31 equals minus 2.7 Newton plus 1.2 Newton equals minus 1.5 Newtons. Oriented in negative x direction. Example number 2. Electric force using vector components. Calculate the net electrostatic force on charge Q3 shown in figure below due to the charges Q1 and Q2. The diagram is shown here. It is given that we have a charge Q1 with magnitude minus 86 microcoulomb, a negative charge, charge Q2 positive charge, and the charge Q3 positive charge. The charge Q3 is a charge of interest, and the charge Q1, charge Q, and the charge Q2 will exert forces on charge Q3. First, we plot the orientation of the forces. Since Q1 is negative and Q3 is positive, then Q3 will be attracted by Q1. It's the reason why the force on charge 3 due to charge 1 is oriented towards Q1. Since charge Q2 is positive and charge Q3 is positive, then the two charges will repel each other, which means that charge Q2 will repel away charge Q3. It's the reason why the force on charge 3 due to charge 2 is oriented in a positive y direction. Then it is given that the direction of the force on charge 3 due to charge 1 is 30 degrees. This angle will be used to determine the x component of this force on charge 3 due to charge 1 and its y component. Then this is the summary of these forces, which means that this is the force on charge 3. It is by vector form that these forces are added by using the parallelogram method. We plot a parallel to the force F31 and starting from the tip of the force F32. From the tip of this vector F31, we plot a parallel to F32. and then these two forces where meet is where we have the tip of the resultant vector. The resultant vector is the resultant force, this one, which is the force on charge 3, which is given in this right diagram B. Then our question mark is to determine this force. Then as you see, we obtain this force by adding the force on charge 3 due to charge 1 to the force on charge 3 due to charge 2. Then the force on charge 3 is equal to the force on charge 3 due to charge 1 plus the force on charge 3 due to charge 2. Then here we need first to calculate the magnitude of these forces by applying Coulomb's force. The Coulomb's force between charge I and charge J is equal to K Coulomb's constant times the magnitude of charge Qi times the magnitude of charge Qj divided by the square of the distance between the two charges. Then here the distance between charge 1 and charge 3, 60 centimeters. Distance between charge 2 and charge 3 is given to be 30 centimeters. Then we are going to perform calculations as follows. The force on charge 3 due to charge 1 equals to K Q3 Q1 over R31 squared equals 9 times 10 to power 9 times 6.5 Q3, 6.5 times 10 to power minus 5 times 8.6 times 10 to power minus 5 divided by 0.6 squared, which gives a magnitude of 140 newtons. And the force on charge 3 due to charge 2 equals to K times the magnitude of charge 3, magnitude of charge 2, divided by the square of the distance between charge 3 and charge 2. K equals 9 times 10 to power 9 times charge 3, 6.5 times 10 to power minus 5 times 5 times 10 to power minus 5 divided by 0.3 squared, which gives a magnitude of 330 newtons. Then we need to resolve the force F31 because this force has two components. It is a force in the fourth quadrant. It is a force in the XY plane. Then its X component is equal to the magnitude of the force F31 times cosine of 30 degrees, which gives 120 newtons. The Y component of the force on charge 3 due to charge 1 is oriented in negative Y, minus the magnitude of F31 times the sine of 30 degrees, because we project this force in a direction where the angle is not given, then minus 17 newtons. The force on charge 3 due to charge 1 due to charge 2 is oriented along a y-axis. This means that this force on charge 3 due to charge 2 along x-axis is equal to 0, because it is equal to magnitude of this force times the cosine of 90 degrees. Why cosine of 90 degrees? It's because between x and y axis there is an angle of 90 degrees, and we know that this cosine of 90 degrees is equal to 0. Cosine of 90 degrees is equal to 0. It's the reason why the x component of this force on charge 3 due to charge 2 is equal to 0, because this force is along the y-axis, and the y component of this force on charge 3 due to charge 2 is equal to the same magnitude of this force. So we are going to add x component of F31 to the x component of F32. Then multiply it by unit vector I, and we will add y components apart from x components. And we have the x component of the force on charge 3 is equal to F3x equals 120 Newton. This is because F32 along x-axis is equal to 0. And the F3y is equal to F3y plus F31 in y direction. We have seen that F3y is equal to the same magnitude of F3, equal to 330 newtons minus 70 newtons, 260 newtons. And the magnitude of this force on charge 3 is equal to the square root of x component squared plus y component squared, which is equal to 290 newtons. And the angle theta means the direction of this force F3. Then this theta means an angle that this force F3 means the force on charge 3 with positive x-axis, with positive x-axis. Then this angle theta is calculated by taking its tangent, which is equal to y component divided by x component. 260 newtons divided by 290 newtons. Then this is equal to 2.2. Then theta is equal to arctan of 2.2, which is equal to 65 degrees. Then question number 3. Consider 3-point charges located at the corners of a right angle triangle as shown in figure on the right side, where charge Q1 is equal to the charge Q3 is equal to 5 microcoulombs, and the charge Q2 equals minus 2 microcoulombs. And this side on this distance A is equal to 0.1 meter. We are asked to determine the resultant force exerted on charge Q3. This question is similar to the previous questions, and we are going to find its answer as follows. Here we are asked to determine the force on charge Q3. This means that charge Q3 is a charge of interest. The charge Q3 is positive, the charge Q1 is positive. This means that charge Q1 will repel charge Q3. This is because like charges repel each other. Then charge Q2 as being a negative charge and charge Q3 a positive charge, charge Q3 will be attracted by the charge Q2. Then this is a force that charge Q2 exerts on charge Q3, and this is the direction of the force that charge Q1 exerts on charge Q3. Then we are asked to determine the resultant force on charge Q3. As we did on a previous question, the resultant force may be plotted geometrically by finding the resultant of the parallel of charge of the force or that charge Q1 exerts on charge Q3, and then plot a parallel to the force that charge Q2 exerts on charge Q3 and form a parallelogram as follows. Then the resultant force is a force which has the origin on charge Q3. It is a force which is oriented in such direction. Then this is the resultant force on charge Q3 due to charge Q1 and charge Q2. Then this force on charge Q3 geometrically as a vector quantity is equal to the force on charge Q3 due to charge 1, or we can use this notation in this book. The force that charge Q1 exerts on charge Q3 plus the force that charge Q2 exerts on charge Q3. We see that charge Q3, the force that charge Q1 exerts on charge Q3 is in XY plane and makes an angle theta with x-axis. Let us say this is an x-axis, and we may plot a y-axis in this direction. Then this force that which is an interaction between charge Q1 and charge Q3 has two components. It has an x component and a y component, while the force that charge Q2 exerts on charge Q3 is oriented in negative y direction. Then we first find the magnitude of these forces by applying Coulomb's law, where the force between charge I and charge J is equal to Coulomb's constant times the magnitude of charge 1 times charge I times the magnitude of charge J divided by the square of the distance between the two charges. Then here it is said that this side means the distance between charge Q2 and charge Q3 is equal to A, which is equal to the same distance between charge Q2 and charge Q1. And here we have a triangle. This is an isosceles triangle. If we have an isosceles triangle, this angle is equal to 90 degrees. And we know that the entire angle, the total angle in a triangle is 180 degrees. If this side is equal to this side, this angle is equal to 45 degrees, and this angle is also equal to 45 degrees. This means that this angle theta is equal to 45 degrees. Why is it equal to 45 degrees? According to geometry, this angle is equal to this angle, the same as this angle. This is also equal to 45 degrees. Then in solution, we first note the direction of these individual forces as shown here, and then calculate the magnitude of these individual forces as follows. Then the magnitude of the force that charge Q2 exerts on charge Q3 is given by the force on charge the force that charge Q2 exerts on charge Q3 equals to Coulomb's constant times magnitude of charge 2, magnitude of charge 3 divided by the square of the distance between charge Q2 and charge Q3. This is approximately 8.99 times 10 to the power 9 times 2 times 10 to the power minus 6 times 5 times 10 to the power minus 6 divided by 0.1 squared. Then this has a magnitude of 9 newtons. This is the force that is exerted on charge 3 due to charge 2. And the magnitude of the force exerted by charge Q1 on charge Q3 is equal to Coulomb's constant times the magnitude of charge 1, magnitude of charge 3 divided by square root of 2 times A squared. The answer gives that this force that charge Q1 exerts on charge Q3 is equal to 8.99 times 10 to the power 9 times 5 times 10 to the power minus 6 times 5 times 10 to the power minus 6 over 2 times 0.1 squared, which is equal to 11 newtons. We are done by calculating the magnitude of these forces. We have seen that the force on charge 3 due to charge 2 is oriented in negative y, which means that it has a 0 y component. And the force on charge 3 due to charge 1 makes an angle of 45 degrees with x-axis. Then we need to find the y component and the x component of the force that charge Q1 exerts on charge Q3. Then it is equal to, the magnitude is the same. This is equal to the F13 along x-axis, which is equal to the same force, the force that charge Q1 exerts on charge Q3 along y-axis, because cosine of 45 degrees is equal to the sine of 45 degrees. And since the magnitude doesn't change, so the y component and the x component of the force that charge Q1 exerts on charge Q3 is the same. Then the x component of the force on charge 3 is equal to x component of the force that charge Q1 exerts on charge Q3 plus the magnitude of the force on that the charge Q2 exerts on charge Q3, but in x direction. And we saw that this force is oriented in negative x. It's the reason why we take 7.9 newtons minus 9 newtons, which is equal to minus 1.1 newtons. And we have seen that this force F32 is oriented along x-axis. Its y component is equal to this force F3y, F32 times the cosine of 90 degrees, because this force is along x-axis and we need to find its y component. Then we need to multiply by cosine of 90 degrees, because 90 degrees is the angle between x and y axis. Then this is equal to 0. It's the reason why the y component of the force on charge 3 is equal to the y component on charge 3 of the force on charge 3 due to charge 1, which is equal to 7.9 newtons. And then this force on charge 3 is equal to its x component times unit vector I plus its y component times the unit vector j. This is in a vector form. And then you may determine its magnitude. The magnitude of this force is equal to x component squared F3x squared plus F3y squared. Then you find its square root. Yeah, then question number 4, calculation of electric field at a point between two charges. 2-point charges are separated by a distance of 10 centimeters. One has a charge of minus 25 microcoulomb and the other plus 50 microcoulomb. We are asked to determine the direction and the magnitude of the electric field at a point P. between the two charges, that is 2 centimeters from the negative charge as shown in this figure below. We have a point charge at point P. Then the separation between the two charges is 10 centimeters, which means that charge Q1 is at 2 centimeters from point P, and the charge Q2 is at 8 centimeters from point P. Since charge Q1 is negative, we know that the direction of electric field is such that the electric field is oriented towards the negative charge. It's the reason why the electric field due to charge 1 is oriented towards charge Q1. And the electric field is oriented away from the positive charge. It's the reason why the electric field due to charge 2 is also oriented to the left. And then by calculation, we have that the electric field is equal to K times the magnitude of the charge divided by the square of the distance between the charge and the point where the field is calculated. So the total electric field is equal to KQ1 over R1 squared plus KQ2 over R2 squared. Then K is common because K times Q1 over R1 squared plus Q2 over R2 squared. R1 equals 2 centimeters, R2 equals 8 centimeters. It's the reason why we have the total electric field at point P is equal to 9 times 10 to the power 9 times 25 times 10 to the power minus 6 over 2 times 10 to the power minus 2 squared plus 50 times 10 to the power minus 6 coulombs divided by 8 times 10 to the power minus 2 meter squared, which gives this total electric field at point P to be 6.3 times 10 to the power 8 Newton per coulomb. Question number 5. Calculation of electric field above 2-point charges. Calculate the total electric field at point A in the figure below due to both charges Q1 and Q2. This is a superposition method. We have two charges, charge Q1 negative charge, charge Q2 positive charge, and we are given a point A. We are asked to determine the total electric field at point A due to these two charges. The electric field at point A is equal to the electric field at point A due to charge 1 plus the electric field at point A due to charge 2. We know how to calculate this electric field. Electric field is equal to K times the magnitude of the charge divided by the square of the distance between the charge and the point where the electric field is calculated. Here, we need to first consider the direction of the individual electric fields. The electric field due to charge 1 is oriented towards the first charge because the first charge is negative, and we know in the theory that the electric field must be oriented towards the negative charge. And the electric field due to charge 2 is oriented away from charge Q2 because charge Q2 is positive. Then this electric field due to charge 1 is having an angle theta with x-axis below x-axis, which means that it has a positive x component and a negative y component. But the electric field on point A due to charge 2 is oriented along the y-axis, which means that it has only a y component and its x component is equal to 0. Then step by step on calculation. We first calculated the electric field on point A due to charge 1, which is equal to K times the magnitude of charge 1, then divided by the distance between charge 1 and point A squared, which gives 1.25 times 10 to the power 6 Newton per Coulomb. Then the electric field on point A due to charge 2 equals to K times the magnitude of charge 2, then divided by the square of the distance between charge 2 and point A, which gives 5 times 10 to the power 6. After determining the individual electric fields, we need to find their X and Y components. The X component of the total electric field on point A is equal to the X component of electric field due to charge 1, which is equal to electric field EA1 times cosine of 30 degrees. We have seen that the X component of this X component of electric field on point A due to charge 2 is equal to the magnitude along X axis. This is equal to magnitude of this electric field on point A due to charge 2 times the cosine of 90 degrees. Why cosine of 90 degrees? It's because this electric field is along a y-axis, and we know that y-axis makes an angle of 90 degrees with x-axis, and then cosine of 90 degrees is equal to 0. 0 times any number gives 0. Then the x component of the total electric field is equal to x component of electric field due to charge 1. And the y component of the total electric field is equal to magnitude of the electric field due to charge 2, because it is oriented along a positive y, minus the y component of the electric field due to charge 1, because this electric field due to charge 1 has a y component oriented in negative y, which is equal to EA1 sine of 30 degrees. Sine because we project EA1 in a direction where the angle is not given. Then this has a magnitude 4.4 times 10 to the power 6. In a similar way to the previous questions, the magnitude of this force or magnitude of this vector electric field on charge on point A is equal to square root of x component squared plus y component squared, which is equal to 4.5 times 10 to the power 6 Newton per Coulomb. And its direction is given by tangent of an angle that this electric field makes with x-axis, which is equal to the y component divided by x component. Y component 4.4 times 10 to the power 6 Newton per Coulomb, x component 1.1 times 10 to the power 6 Newton per Coulomb, which gives the 4. Then phi is determined as an arctan of 4, which is equal to 76 degrees. Question number 6. A charge Q1 equals plus 7 microcoulomb is located at the origin here of x and y axis, and a second charge Q2 is located at a distance 0.3 meters from the origin along x axis. Find the electric field at the point P, which is located at a distance 0.4 meters along positive y axis. This means that we have to calculate the electric field at point P, electric field at point P due to charge Q1 and charge Q2. Geometrically, this vector electric field at point P equals to the vector electric field at point P due to charge 1 plus the electric field at point P due to charge 2. To calculate the electric field, we need K, Coulomb constant, times the magnitude of the charge. The charges are given. Charge Q1 is 7 coulombs, charge Q2 minus 5 microcoulombs, divided by and the square of the distance. The separation between each charge and the point P is given. So we first orient these electric fields. Charge Q1 is positive, then the electric field due to a positive charge is oriented away from the positive charge. So the reason why the electric field due to charge 1 is oriented along positive y. And the electric field due to a negative charge is oriented towards that negative charge. It's the reason why this electric field 2 is oriented towards the charge Q2. Then step by step in calculation, the electric field due to charge 1 equals K Q1 over R1 squared, which gives a magnitude of 3.9 times 10 to the power 5 Newton per Coulomb. The electric field due to charge 2 equals K Q2 over R2 squared, which gives the magnitude of 1.8 times 10 to the power 5 Newton per Coulomb. Then here the vector electric field has only the vector electric field due to charge 1 is oriented along the y-axis, which means that it has only a y component, while the vector electric field E2 is in the xy plane, which means that this one is having two components. It has an x component which is equal to E2x is equal to magnitude of E2 times the cosine of an angle theta. It is said this angle theta is equal to the same angle theta. So cosine of this angle theta is equal to what? It is equal to adjacent side divided by hypotenuse, 0.5 divided by 0.3. Then this is equal to 5 over 3. And this electric field due to charge 2 has a y component oriented in a negative y direction. E2y is equal to minus magnitude of E2 times the sine of this angle theta. Why sine? It's because when projecting this vector E2 along the y-axis, we project it in a direction opposite to the given angle, where the angle is not given. And this sine of the angle theta may be calculated from this triangle Q1, Q2, P. Sine theta is equal to opposite side divided by hypotenuse. Opposite side is equal to 0.4 meters divided by hypotenuse 0.5. Here in the first Then this one is equal to 4 divided by 5. And in the first part we did a little mistake. Then we have cosine is equal to adjacent side divided by hypotenuse. Adjacent side is 0.3 divided by hypotenuse is 0.5, means 3 over 5. It's the reason why we say that the x component of E2 is equal E2 cosine theta equals 3 over 5 times E2, and the y component of E2 is negative equals minus E2 sine theta equals minus 4 over 5 E2. Hence E1 is equal to 3.9 times 10 to the power 5 along j times j, means it is along a y-axis. E2 equals 1.1 times 10 to the power 5 times unit vector I minus 1.4 times 10 to the power 5 times unit vector j, because these are vectors. And we have seen that the total electric field at point P is equal to electric field at point P due to charge 1 plus electric field at point P due to charge 2, which gives, we add x components apart from y components. X component is 1.1 times 10 to the power 5, and the x component is 3.9 minus 1.4, which is equal to 0.5 times 10 to the power 5 Newton per Coulomb. Then you may determine the magnitude of this electric field to be equal to the square root of Ex squared plus Ey squared. Then you may take a square root of 1.1 times 10 to the power 5 squared plus 2.5 times 10 to the power 5 squared in Newton per Coulomb. Then as the magnitude becomes 2.7 times 10 to the power 5 Newton per Coulomb. Additional exercise. Find the electric force exerted on a charge of 2 times 10 to the power minus 8 coulombs located at P. To find this electric force, we need to apply the formula between the electric force, which is equal to the charge, times the electric field. This means that this electric force is equal to charge is equal to times 10 to power minus 8 coulomb times the electric field at point P equals 2.7 times 10 to power 5 Newton per Coulomb, and the force will be in newtons, which is equal to 5.4 times 10 to power minus 3 newtons. 5.4 times 10 to power minus 3 newtons. And question number 7. For a circuit of figure on the right side below, where capacitance C1 equals 6 microfarad, capacitance C2 1 microfarad, capacitance C3 3 microfarad, and capacitance C4 12 microfarad as shown in this diagram. We are asked to determine the equivalent capacitance, the charge and potential difference across each capacitor. Then as solution, we need to write down the given data and to be found. And then we need to write down the equation to be used. We first simplify the diagram. Since the capacitor C2 and the C3 have the same voltmeter V23 to measure the voltage across capacitor 2 and across capacitor 3. This means that capacitor C2 is in parallel connection with capacitor C3, and their combination will be in series with C1 and C4. Then we first simplify the capacitors in parallel connection. In parallel connection, the capacitors are obtained by algebraic sum of individual capacitors. It's the reason why here we have the equivalent capacitance of the parallel combination C2 and C3 is given to be C23, because C2 plus C3. This C23 will be in series with C1, C2, and C4. Then here the capacitance C2 equals 1 microfarad, C3 3 microfarad. Then the equivalent capacitance of the parallel connection 2 and 3 is 4 microfarad. And the net equivalent capacitance means the equivalent capacitance of the circuit is obtained by considering that the capacitance C1, C23, and C4 are connected in series. In series connection, we use the inverse relationship. It's the reason why inverse of equivalent capacitance equals inverse of capacitance 1 plus inverse of capacitance 2, 3 plus inverse of capacitance 4 equals 1 over 6 plus 1 over 4 plus 1 over 12, which is equal to 1 over 2. Then this equivalent capacitance equals 2 microfarad. And in number B, we are asked to determine the charge and potential difference across each capacitor. Here, let us plot roughly our diagram, our electric circuit. This is capacitor 1, and here is the capacitor of the parallel combination, and here we have the battery and the capacitor C4. It is clear that these capacitors C1, C23, C4 are in series. In series connection, we have the voltage, means the potential difference to the terminals of the battery V, which is equal to the voltage to the terminals of the first capacitor plus the voltage to the terminals of this capacitor 2, 3 plus the voltage to the terminals of the fourth capacitor. Then and the charge which is released by the battery is the same charge Q1, which is stored by capacitor 1, and the same charge that is stored by capacitor 2, 3, and the same charge stored by capacitor 4. It's the reason why here we say that Q1 is equal to what? Q2 is equal to what? Q3, Q4. V1, V2, V3, and V4 are equal to what? Then the equations to be used are these. Then for the series connection, we have a series connection C1, C23, and C4 are in series, which means that capacitor charge Q1 equals to charge Q3 23 means Q2 plus Q3 equals charge Q4, which is equal to the total charge which is flowing through the circuit. And the total charge is equal to equivalent capacitance times the voltage to the terminals of the battery. The equivalent capacitance equals 2 microfarad, where the potential difference to the terminals of the battery is equal to 48 volts. Then the total charge equals 6 microcoulomb. Then charge 1 means the charge stored in capacitor 1 equals to the charge stored in capacitor 4, which is equal to the total charge, which is equal to 96 microfarad. And then to find the charge stored by capacitor 2 and capacitor 3, we need to determine their common potential difference, because here this potential difference, which is to the terminals of the battery, is equal to the potential difference to the terminals of capacitor 1 plus potential difference to the terminals of the combined capacitors 2 and 3 plus the potential difference to the terminals of the fourth capacitor. And here this voltage to the terminals of the combined capacitors 2 and 3 is the same voltage to the terminals of the second capacitor, and it is the same voltage to the terminals of the third capacitor. Then we know that to determine the voltage, here the general formula states that the voltage is equal to the charge divided by the capacitance. Since capacitance C1 and the capacitance C4 are given, we may determine capacitance, potential difference 1, which is equal to charge 1 over capacitance 1 equals 16 volts. And the potential difference across the fourth capacitor is equal to charge 4 divided by capacitance 4, which is equal to 8 volts. Then we may determine this voltage in parallel connection to be the voltage across the battery minus the voltage across the first capacitor minus the voltage across the fourth capacitor. It's the reason why the voltage across these two capacitors 2 and 3 is equal to 24 volts. And then since the charge is equal to the capacitance times the voltage, it's the reason why charge 2 equals capacitance 2 times voltage 2, which is equal to 1 microfarad times 24 volts equals 24 microfarad. And the charge 3 equals the capacitance 3 times the potential difference 3 equals to 3 microfarad times 24 volts equals to 72 microcoulomb. And finally, we can verify that this total charge is equal to charge 2 plus charge 3, 24 microcoulomb plus 72 microcoulomb equals to 96 microcoulomb. Then question number 8. We are asked to determine the charge and the voltage on capacitors. Determine the charge on each capacitor and the voltage across each capacitor in the figure below, where the capacitance C equals 3 microfarad and the battery voltage is 4 volts. We are given the voltage of the battery to be 4 volts. Capacitance C1 equals the capacitance C2 equals capacitance C3 equals to the capacitance C, which is equal to 3 microfarad. This question is similar to the previous one, where we will have capacitance capacitor 2 and capacitor 3, which will be combined in one capacitor in parallel connection, and their combined capacitor will be in series with capacitor 1, and this will be in series connection with the battery. And then we may determine this C23 is obtained by algebraic sum of capacitance 2 plus capacitance 3, which is equal to 6 microfarad. And since capacitance C1 is in series with capacitance C3, to determine the equivalent capacitance in series connection, we use inverse relationship. Means inverse of equivalent capacitance is equal to inverse of capacitance 1 plus inverse of capacitance 2, 3, which is equal to inverse of 3 microfarad plus inverse of 6 microfarad. Then the common factor is 6. 6 divided by 3 gives 2. 2 times 1 gives 2. 2 plus 1 gives 3. 3 over 6 equals 1 over 2. Then equivalent capacitance becomes 2 microfarad. We are done with calculation of the capacitance of the equivalent capacitance across this circuit. But we are asked to determine the charge on each capacitor. And then here we see that the battery will release a charge Q. This charge which is released by the battery is the same charge which is stored in the combined capacitors 2 and 3, and the same charge which is stored in the capacitor 1, where this Q is equal to Q to 3, which is equal to Q1, and this total charge is equal to equivalent capacitance times the voltage across the terminals of the battery, which is equal to this is equal equivalent capacitance 2 microfarad, 2 times 10 to power minus 6 farad times the voltage across the battery is 4 volts times 4 volts. Here we need to first express the capacitance in SI unit and then convert microfarad into farad. 1 micro equals 10 to power minus 6. It's the reason why this charge equals to the charge Q1 stored by capacitor 1, which is equal to the charge stored by the parallel combination is equal to 80 microcoulomb, as shown in detail here. Then the total charge is equal to equivalent capacitance times the voltage to the terminals of the battery, which is equal to 80 microcoulomb. So Q1 equals 80 microcoulomb, and since the voltage is equal to charge divided by capacitance, V1 equals Q1 over C1 equals 80 microcoulomb divided by 3 microfarad equals 2.7 volts. Then V2 and V3, here to determine V2 is easy, equals Q2 over C2. Then how do we determine Q2 and Q3? Q2 is equal to Q3 equals 1 over 2 the Q, because these capacitors 2 and 3 are initially in parallel and they have the same capacitance. This is capacitor 2 and this is capacitor 3, which are in parallel and then be in series with capacitor 1. This is our original circuit. This is our original circuit. Then this means that as we have calculated the charge here, the charge that Q23 is the charge is divided into the charge which is stored in capacitor 3 and the charge which is stored in capacitor 2. Then here we may determine the voltage of the parallel connection V23. This is equal to the voltage to the terminals of the battery minus the voltage to the terminals of the first battery. Then the voltage to the terminals of the first battery equals to the charge that is stored in battery 1 divided by capacitance 1. The charge stored in capacitance 1 is equal to 8 microcoulomb and the charge 1 is equal to 3 microfarad. Then this will give you approximately 2.7 volts. And then if you take this V23 means the voltage across the parallel connection, which is equal to the voltage across the battery, which is equal to 4 volts minus the voltage across the first capacitor 2.7 volts will have 1.3 volts. And we are asked to determine the charge Q2 and the charge Q3. The charge Q2 is equal to capacitance 2 times voltage 2. This is because the voltage 2 is equal to the voltage across the third capacitor, which is equal the same voltage across the parallel connection, because in parallel connection the voltage is the same, which is equal to 1.3 volts according to our calculation. Then this charge across capacitor 2 equals capacitance 2 is equal to 3 microfarad, then times voltage 2 equals 1.3 volts, which is equal to approximately 3.9 microcoulomb, then which is approximately 4 microcoulomb. Then in a similar way, Q3 is equal to capacitance 3 times voltage 3. Since capacitance 2 is equal to the capacitance 3 and voltage 2 is equal to voltage 3, this will be equal to 3.9 microcoulomb. And here we make an approximation of 4 microcoulomb. Question number 9. Find the equivalent capacitance between point A and B for the combination of capacitors shown in the figure below. All capacitances are in microfarad. We are given such a diagram. As a solution, we first take the capacitance 2 and the capacitance 3 to be in a parallel connection. Once they are in a parallel connection, we know that the equivalent capacitance of 2 and 3 will be capacitance 2 plus capacitance 3. Then we have 1 microfarad plus 3 microfarad equals 4 microfarad. Then we take capacitance C4 and capacitor C4 and capacitor C5 to be in parallel, and we simplify them into a 1 capacitor with capacitance 5, which is equal to capacitance 4 plus capacitance 5. Capacitance 4 is equal to 6 microfarad plus 2 microfarad equals 80 microfarad. And here we have then a series connection of 4 and 4 microfarad and a series connection of 80 and 80 microfarad. Let us say 1 and here say 2. In 1 we have the equivalent capacitance here will be equivalent capacitance of the series connection. In series connection we use inverse relationship. So there is a capacitance 1, 2 and 3. Capacitance 1, 2 and 3. Its inverse is equal to inverse of capacitance 1 plus inverse of capacitance 2 and 3. Then this is equal to 1 over 4 microfarad plus 1 over 4 microfarad, which is equal to 2 over 4. Then inverse of 2 over 4 becomes 2. Then this gives that the equivalent capacitance of capacitor 1, 2 and 3 is equal to 2 microfarad. And in B, in 2, we have capacitance of capacitor 4, 5 and capacitor 6. They are in series. Once capacitors are in series, to find their equivalent capacitance, we use an inverse relationship. Inverse of capacitance 4, 5, 6 is equal to 1 over capacitance 4, 5 plus 1 over capacitance 6. Then this is equal to 1 over 8 microfarad plus 1 over 8 microfarad, which is equal to 2 over 8 microfarad. Then this capacitance 4, 5, 6 is equal to 4 microfarad. 4 microfarad. Then which is this? This is the capacitance 4, 5, 6. Means the combination of capacitors 4, capacitor 5, capacitor 6. And this is the combination of capacitor 1, capacitor 2 and capacitor 3. Then this capacitance, the capacitor 1, 2, 3 and capacitor 4, 5, 6 are in a parallel connection. Once they are in a parallel connection, we'll have the equivalence capacitance in a parallel connection is obtained by algebraic sum of individual capacitances, which is equal to C1, 2, 3 plus capacitance 4, 5, 6, which is equal to 2 microfarad, 2 microfarad plus 4 microfarad, which is equal to 6 microfarad. This is the equivalent capacitance of the circuit, 6 microfarad. This is how you will answer to such questions. Then question number 10, energy stored in a capacitor. A camera flash unit stores energy in a 150 microfarad capacitor at 200 volts. First, how much electric energy can be stored? B. What is the power output if nearly all this energy is released in 1 millisecond? First of all, we are given the capacitance and the voltage. The formula for energy is the half of the product of capacitance and the square of the voltage. Capacitance is given, voltage is given. Remember to change the capacitance in farad. Microfarad is equal to 10 to the power minus 6 farad, and the square of voltage equals 3 joules. Then in sub question B, we are asked to determine the power. The power is equal to energy divided by time. The time is given to be 1 microsecond. 1 microsecond equals 10 to the power minus 3 seconds. Then the power is equal to energy 3 joules divided by 1 times 10 to the power minus 3 seconds, which is equal to 3000 watts. Then question number 11, we are given 3-point charges, Q1, which is equal to 1 microcoulomb, Q2 minus 2 microcoulomb, Q3 plus 3 microcoulomb, which are located at the points indicated in this figure on the right. We are asked different things. A. What is the total electric potential at point P? What is the potential due to charge Q1, charge Q2, and charge Q3 at point P? We know that the electric potential by definition is equal to K times the charge divided by the distance R from the charge to the point where the potential is calculated. Then and the total potential is equal to a sum of individual potentials. Sum I varies from 1 to n. It's the reason why the potential at point P equals to the potential at point P due to charge 1 plus potential at point P due to charge 2 plus potential at point P due to charge 3 equals KQ1 over RP1 plus KQ2 over RP2. RP2 is 5 meters because here we have a rectangle and the diagonal of the rectangle is given to be 5 meters, where the distance between Q1 and P is 4 meters, plus KQ3 over RP3, where RP3 is 3 meters. And in sub question B, we are asked to determine the work an external agent must provide to bring a charge Q4 equals 2.5 microcoulomb at a constant speed from infinity to the point P. This is the electric potential energy. And then here we need to explain this detailed solution, where the potential at point P equals K times 10 to the power 9. All the charges are in micro, so they are multiplied by 10 to the power minus 6, then times 1 inverse the charge times the distance. Charge 1 is 1 over distance, for distance between charge 1 and the point P, minus 2 over 5. Charge 2 equals minus 2 microcoulombs, plus 1 because charge 3 is equal to 3 microcoulombs, and the distance between charge 3 and the point P is 3 meters. And then we'll have that the potential at point P equals 7.65 times 10 to the power 3 volts. Then number B, we are asked to find the work done by an external agent to bring a charge Q4 from infinity to the point P. This work done is equal to the charge 4 times the potential difference at point P, equals charge Q4 was 2.5 times 10 to the power minus 6 times the potential at point P, 7.65 times 10 to the power 3, which is equal to approximately 19.13 millijoules. In subquestion C, we are asked to determine the total electric potential energy for the system made of the 3 charges Q1, Q2, and Q3. We know that the formula for potential energy between 2 charges I and J, this is equal to K Qi Qj divided by the distance Ij, means the distance between I and J. And here you have the potential between charge 1 and charge 2 plus potential electric potential energy between charge 1 and charge 3, and the electric potential energy between charge 2 and 3, which is equal to K Q1 Q2 over I12 plus K Q1 Q3 over I13 plus K Q2 Q3 over R23, which is equal to minus 1.41 times 10 to the power minus 2 joules. And we are ending the hints on exercises regarding electrostatics. Thank you for watching. We'll meet you tomorrow.